And now I give to you Christopher Kelson.
Hi, Lindsay. Thank you, everybody, and thank you for the introduction. My name is Chris Kelson, and I'm the senior geologist here at Atlantic Testing Laboratories. Again, I thank you all for taking a little bit of time out of your busy day today to join me for this webinar. So here at ATL, I'm in charge of everything and anything related to geology. So I obviously deal a lot with just the rocks and the minerals and the field mapping end of things, but I also do a lot of petrographic analysis of rocks and minerals, as well as concrete and air void analysis of concrete. So that's what I do here at ATL, and I've put together two of these webinars that deal with geologic hazards. And the point of these two webinars, this is part two we're dealing with today, but the point of these two webinars is for me to have an opportunity to kind of give you the geologic explanation for a lot of engineering type situations and things that you see on a daily basis. So, you know, we could be here for days and days and solid weeks talking about these things. We'll cover this very topically in the next hour or so. So, excited to do it. This is always a fun presentation. And just to reiterate what Lindsay mentioned, you know, we'll have a couple really difficult questions presented to you throughout the webinar. They're timed, answer them, and we'll move on. But just a heads up that that you'll run into a couple of those things as we go through this. So just a brief definition of what a geologic hazard is in the first place. Any earth material, geologic event or process that is hazardous or potentially hazardous to either life or property. Earth materials include, you know, water, minerals, soil, rocks, etc. Geologic events, things like landslides, earthquakes, volcanic eruptions, and of course, kind of subsets of those things like tsunamis and seiches and noyades and lahars. And then geologic processes, which of course includes weathering of rocks and erosion and karst, etc. So pretty much anything you can imagine from a geologic perspective could potentially be hazardous to life or property. The purpose of this whole thing, big overarching purpose of this discussion is basically to reiterate the fact that identifying these hazards allows us to prepare for them and maybe mitigate them for when they do occur. That's probably a better option than trying to react to one of these events that has occurred and then trying to, you know, clean up after it. And also, just to, before I forget, because I don't have a laser pointer or a piece of chalk writing on a chalkboard here for everybody, you'll see my mouse cursor moving around to point things out, so please keep an eye on that. So this particular webinar is focused on water, and in particular, we'll discuss floods and also discuss a little bit about rivers. So geologic hazards associated with water is the theme of today's webinar. A brief non-official definition of a flood. Here we're gonna say that basically any point when you have the elevation of water that's greater than the elevation of land that's normally dry, we're gonna call that a flood. And this can occur due to water rising in an enclosed body of water, such as ocean, lakes, reservoir, right, rivers or streams. We could also talk about flooding associated with the rise of the water table, right? So the rise of groundwater and the level of the water table. And then the third bullet there, if we consider a certain volume of liquid water that over a period of time is then introduced onto the Earth's surface, if that volume of water over that unit of time exceeds the ability of the soil to essentially accommodate that same volume of water over that same period of time, then we have then we could have a flood. So those are three basic ideas that we'll be approaching today. It's also important to understand that floods can be caused by Mother Nature as well as humans, right? So these are natural and/or anthropogenic features, and sometimes it's a tag team between the two, or a perfect combination of two things working together. So during the course of this webinar, we'll be discussing a little bit of each of these 6 bulleted points: climate change, water management, excessive or intense rainfall, or rapid snowmelt, right? We're talking about liquid water on the Earth's surface. Flooding due to weather or storms, the subsidence of land, and we'll talk about watersheds, or AKA drainage basins, and their geological characteristics as well. And that discussion will include some discussion about rivers and streams. So let's start off with tackling the concept of climate change. And I know that's a big buzzword in political circles, and it's a big buzzword, has been for a while. Here, we're simply addressing this from a strictly scientific standpoint, and I just want to say 1 or 2 things about the idea of climate change. First of all, the Earth's climate is not static. I mean, by definition, it changes. It's not the same all the time, and it's never been the same all the time. So climate change happens on a general scale anyway, right? The biggest discussion point these days, pointing out or trying to explain climate change, is in this case discussing the amount of carbon dioxide in our atmosphere. Carbon dioxide is termed a greenhouse gas, meaning that the more concentrated it is in our atmosphere, it lessens the planet's ability to re-radiate heat back into space, right? So the Earth's surface just gets warmer and warmer, and the heat can't dissipate back out into space, and that's the greenhouse effect. And carbon dioxide is one of those gases that enables that to happen. On a very extreme case, for example, the planet Venus has its atmosphere, which is 96% CO2, and the surface of Venus is so hot because of the greenhouse effect that you can melt lead on the surface of Venus. Here on Earth, the amount of CO2 in our atmosphere is less than 1%, so it's relatively not as bad as it could be, right? But it's still a player, and it's definitely the amount of CO2 in our atmosphere is definitely correlative to increases in global temperature, right? Things get warmer the more CO2 there is in the air. What I ask everybody to keep in mind is that CO2 in our atmosphere is nothing new, and it's not all there because of humans, and it's been there forever, and Mother Nature naturally puts it into the atmosphere. And when we take a look at the concentrations of CO2 in our atmosphere over the past 400,000 years, you can see that, and so if you take a look at this, at these graphs, that the left side of the graph represents, basically 400,000 years ago, and the red line represents present day, right now, as we're talking to each other. You can see the amount of CO2 in our atmosphere today, but that's about the same as it was 120 years ago, 120,000 years ago, and about 230,000 years ago, and 320,000. So the amount of CO2 rises and falls, and it's done this naturally over time. We know these data from studying trapped atmospheric gases in ancient ice cores. So these are actual measurements. We know how much CO2 is in the atmosphere in the past, several 100,000 years. The red line on the far right of the screen, again, represents us present day, but it also represents essentially the width of that line is even bigger than, say, the amount of time covered by the Industrial Revolution, where we can say humans were really cranking CO2 into the atmosphere, burning petroleum and coal and whatnot. So even with that there, we can still see that over this Earth's immediate past, we've had more CO2 in the atmosphere coming and going. So it's a natural thing. Volcanic emissions, volcanic eruptions puts a lot of CO2 in the atmosphere naturally. You know, the biosphere puts a lot of CO2 in the atmosphere. It also removes CO2. Ocean water sequesters CO2 depending on the temperature of the water. So there are a lot of factors involved. So I'd just like everybody to kind of keep in mind this information next time we hear the whole climate change discussion happening. But basically, the warmer it is on Earth, the more ice and snow melts, and of course that means sea level will rise relative to the land, and that will cause flooding, especially on the coastal areas. So the map that you're looking at now shows a couple things. First of all, it shows where the coastline was 18,000 years ago when things were cooler, right? So more ice and snow means sea level is lower. And we can also see outlined in yellow what the coastline was like 100 million years ago when global warming was such that no ice and snow existed. Sea level rise was at its maximum. And the Arctic Ocean and the Gulf of Mexico essentially connected each other through the interior of the continent. So, you know, you can see the outline of present-day continental United States. And again, sea level rises and falls naturally. The effect of human influence is yet to be fully understood because it just hasn't been happening very long, geologically speaking. Let's switch gears a little bit and talk about flooding with respect to water management. I guess this would be more appropriately called how we can manage water to stop flooding. And one of the and the example we'll use here is the Racket River here in upstate New York. It's 146 miles long, but it's dammed up in 27 different places. The purpose of this, the end result of this, is that we essentially can control the level of the water in this river in any given length of its you know, any given length of it. So if intense water precipitation occurs, a lot of water is entering into the river, we can release it as needed to control flooding. So we have a little bit of a handle on this in this particular example, but that's one way that we can mitigate flooding. Switch gears one more time, talk about what we're calling here excessive and intense precipitation, and we mean rain. Okay, not snow, but rain. This is an interesting chart up until 2012, so it's a 40 or 50 year span here, but basically it's 50 some odd years. But basically it's saying that throughout the continental United States, the heavy downpours, big rain events, a lot of rain over a short period of time have actually been increasing over that span from the late 50s to 2012. So when you're suddenly introducing a lot of water onto the Earth's surface, liquid water onto the Earth's surface over a short period of time, the ground's ability to soak that water in is lessened overall, and the potential for floods increases because of that. And the usual result of throwing a lot of liquid water onto ground that basically just can't absorb it all at the same rate is you get what's called a flash flood. And these are very common in the western United States and the Southwest in particular, where the ground is just baked dry most of the time, and then you get these big intense rainstorms that the water just can't soak into the baked ground, and you have this overland flow that we call a flash flood. Time for question number 1, please.
Back to you, Chris.
Thanks, Lindsay. Okay, question number 1. which of the following is considered a greenhouse gas? That's C, carbon dioxide. There are others, but CO2 definitely gets the lion's share of the publicity due to the burning of fossil fuels, right? Okay, so discussing a few other potential flood-causing mechanisms. Here we have, we'll just call weather or storm, so flooding due to something going on with the atmosphere, right? Some weather. And we know this is, so I'll just show one slide here. This is down around New York City, but there's an actual map that shows where these where flood risk is least and where it's greatest. In this case, due to hurricanes. So you have Mother Nature whipping up the ocean water, right, because of all the winds, and it's blowing the water onto shore that normally doesn't get it. And not surprisingly, the land closest to the water is under more risk of being flooded because of this mechanism than further inland. But it's also a function of how high how high the land is above the sea level to begin with. So these maps exist, and obviously if you live in a place like this, for example, you might want to consult these maps to see if you'll be in a potentially dangerous location. Another mechanism that could cause flooding, in this case, instead of raising the level of the ocean, right, we're actually going to drop the elevation of land. So we're talking about the subsidence of land. And a couple mechanisms, from a geological perspective, a couple mechanisms can make this happen, but we're just looking at the overarching idea here that if the water level is if the elevation of the water surface is constant, but you drop land, right, you're going to cause flooding as well. A great example of this is Venice, Italy, where the entire city is just slowly sinking, right, which is causing flooding as a consequence for that. Okay, let's spend a few minutes and talk about watersheds, also known as drainage basins, because the characteristics, both the geological and physiographic characteristics of drainage basins are really important, and they dictate not only flooding on a local or even regional scale, but it also affects the amount of water that flows out of these drainage basins via streams or rivers. It also dictates how much the underlying aquifers are recharged, how fast they are able to be recharged, and also the quality. And I've highlighted that word in yellow. The quality of water flowing out of a drainage basin is also tied into its geological and physiographic characteristics. So this is a kind of a big topic here we'll be covering next. And I use I highlighted the word quality in yellow because water quality means different things to different people, and it depends on the context in which you're using it. So usually in the discussion of water quality, we're essentially referring to the suitability of water for a particular use. So we all understand kind of intrinsically that if we're drinking the water, we want it to be high quality, whatever that means, but higher quality to drink it. And if we're simply using water to turn an electric turbine to generate electricity, then water quality doesn't have to be so high, right? We just need it to push the turbine blades to generate the electricity. So the whole water quality thing also gets into contaminants and pollutants and what do those words mean, and we're not going to delve into that deeply here. I'm simply stating that the characteristics of a watershed have far-reaching implications that include the quality of water, and we'll touch on little bits of this as we go. So a drainage basin or a watershed, same thing, is simply an area of land that's separated from an adjacent area of land by some topographical divide. So whether that be a mountain range or a series of hills or whatever. In the diagram you're seeing on your screen now, the top diagram, there are two drainage basins next to each other. One is kind of an olive drab green color, and the other one is a lighter green color. But they're separated from each other by this mountain ridge or chain of hills right in between them. The arrows within each of these drainage basins show the pathway for water running over the surface in either one of those drainage basins and where the water would go. So at the end of the day, all water that falls, say within this drainage basin on the left, all surface water will essentially flow out this singular river circled here in red, which is different than the surface water in the adjacent drainage basin flowing out of that particular river, right? And these two drainage basins might be connected with each other downstream, and those two rivers might, down gradient, those two rivers might coalesce into each other, but we're separating them here. Now the aerial extent of each drainage basin could be, tens of thousands of miles, or it could be, a couple feet. So scale is not really important here, but we're getting the idea of how these things work. What's happening on the surface of each of these drainage basins has a direct impact, and probably the most important impact, on if any flooding will occur in these areas. So on the drainage basin on the left, let's just pretend that its surface is basically a big parking lot. It's all paved over with concrete and asphalt, and that's what this drainage basin looks like. Well, if that's the case, then whenever we have rainfall or snowmelt, most of that water will not soak into the ground, right? If that's just normal concrete and asphalt, and most of the water will basically just flow over the surface into the gutters, into the storm drains, and out through a pipe someplace that carries it out of the area, right? The underlying aquifer is not being recharged, or very little recharge is happening, because most of that water is just funneled out, off over the pavement. The drainage basin on the right, let's pretend that the surface of that drainage basin has experienced a major fire, where all of the vegetation and the trees have just been scorched off and burned, and it's just bare soil. So whenever it rains here, the soil is in direct contact with the liquid water. Some of the water will soak into the ground, but there's also nothing holding the soil in place. So here we're going to experience a lot of erosion, right? Mass transport of the sediment on the surface, because there's no vegetation holding it in place anymore. Oops, let's go back. So the water in the rivers coming out of each of these drainage basins will have a definite and different characteristic to them, right? The one on the right will be choked with sediment, and the one on the right will be choked with cigarette butts and oil from cars' engines and garbage and whatever else. Needless to say, both of these are not optimal situations with respect to floods, because again, the water's not soaking into the ground; it's flowing over the surface, and that's potentially problematic. To illustrate that latter point just a little more briefly, and you see these situations happening in the real world frequently, where out west, California, right, a year or two ago, where you have just entire hillsides, entire mountains just scorched clean, and then a lot of water falls onto the area, and a lot of that soil is just mobilized as a big mudslide that goes on down the hill, and very little is infiltrating it into the ground. So again, flooding here, but in this case, it's flooding and mass movement of soil. So not good. And to further illustrate that drainage basin we were exemplifying on the left of that slide 2 slides ago, when imagine this is a drainage basin, which it is. It is completely concreted over. Again, anything on the surface of that concrete is going to get washed into that main river in the bottom, right? And off it goes to you know, to the next you know, to the next place, and it's just full of whatever's in the drainage basin is being carried out by the water. This is a way to control flooding, but it's also again, not letting the water soak into the ground, and the more water that can soak into the ground to recharge the aquifer, the less flooding is going to occur. And this just illustrates that idea one more time. Everything that goes down these big drains that flows out of these big impermeable, relatively impermeable areas, parking lots, for example, or roads or streets or everything, just goes right into the ecosystem usually. So at the end of the day, which is which is better? I mean, which one of these drainage basins would you like to have, live in and live around and be around you? Obviously, a drainage basin shown on the left here, which is full of vegetation and trees and vegetation to hold the soil in place, right? This enhances aquifer recharge. This lessens the potential of flooding, right? Because more water is able to soak into the ground, and at the end of the day, the quality of water coming out of that drainage basin that has all that vegetation is way better compared to the water coming out of the drainage basin that's just coming from the big parking lot. So in order to dig into that one layer deeper, we need to understand a couple concepts that the soil within these watersheds possesses. And we're talking about the porosity of the soil or the subsurface and the permeability of the subsurface. I'm using the word soil here, but it's also applying to rock as well. When we refer to soil, again, I use the word soil and sediment. That is not the same as dirt. Geologically speaking, there's no such thing as dirt, so I'm using soil and sediment, right, instead. But soil, it's a mixture of clay, silt, sand, and gravel. These are all the clastic sediments, right? Fragments of pre-existing rocks and minerals that have been broken down into those particular sizes. The soil can either be well or poorly sorted, geologically speaking. Graded is the engineering term, and the equivalent for that. The angularity of the sediment grains, the composition, and basically the mineralogy of the sediment, any organic matter present in the sediment, therefore into the soil, these all have a big factor with respect to how easily the water can soak into the ground versus flow over the surface. And remember, flowing over the surface is that's more prone to cause flooding issues. So we can think of all clastic sediment as being plotted on a ternary diagram. So at the upper left of this diagram, we have just a listing of all the clastic sediment sizes and how large each of these particles are. At the apex of this diagram, we have the end member. So lower left represents sediment that's 100% clay, top is 100% silt, and the bottom right is 100% clay. And we can have obviously mixtures of different clastic sediment sizes within a particular soil, right? And so just for reference, if we have sediment that's half silt and half clay, by definition, it's either a clayey silt or a silty clay, depending on the exact percentages. Equal percentages of each of these things is loam, right? You've heard the word, now you know what that is, with organic matter as well. But if we take a look at the porosity of these different sediment types, in other words, porosity, we're talking about the percentage of open space within each of these soils. We can see that all across the board, the porosity is relatively high for each of these sediment types. So in other words, a bucket of sand or a bucket of silt or a bucket of clay will all have essentially equal porosities, which are high. They can store a lot of water, for example, because they have a lot of open spaces. The problem is permeability. Well, it's not a problem, but it's a difference here, right? So for permeability, we're talking about the ability of these substances to allow a fluid to move through it, right? How easily a fluid can move through something. So according to this, silt and sand anything on the silt and sand end of the scale is highly permeable compared to something that's rich in clay. What this means is silt and sand and clay can all store a lot of water due to all the open space between the sediment particles. But that water can transmit most easily through silt and sand. Clay not so much. Clay can hold water, but it won't let water flow through it. So it has very low permeability. Meaning that if our soil has a lot of clay to it, we'll have a tendency to not allow a lot of water to soak into the ground, right? Because it can't move through that clay-rich material. Question number 2, please.
Back to you, Chris.
Thanks, Lindsay. Question number 2. The ability of a fluid to move through a medium is called permeability. Just to wrap up our discussion on sediment and sediment sizes, the 5 little block diagrams on the top of this chart basically shows the distribution of different size sediment grains in each of these examples. So on the left, we have something called in geology world we would call that a very well sorted sediment. In engineering world, that would be called poorly graded, right? And then of course on the far right of the scale, the far right diagram is just the opposite. We have something called very poorly sorted from geology, but gap graded with respect to engineering terms. So it's it's obviously easily possible to have different sediment sizes mixed in with each other, and that's important for this part of the discussion. Again, we're talking about how easily water can filter into the ground, right? We introduce a lot of liquid water onto the Earth's surface. How easily does it go into the surface? And this is part of that discussion. So one factor that affects the ability of sediment or soil to accommodate water, right? Therefore prevent flooding, depends on how spherical each of these sediment particles are, as well as how those sediment particles are packed against each other. So on the left, we have a diagram that's referring to sediment particles of about equal sizes, and they're all relatively spherical, and they're stacked against each other in something called a cubic packing arrangement. So if we just connected the center points of four adjacent sediment particles, we were outlining a square. In 3D it'd be a cube. Well, in this example, the porosity of that sediment is almost 50%. Like half of that diagram on the left is actually open space, right? And those open spaces in this case can accommodate water. On the right, we have those same size and same spherical particles, but in the pore spaces, in the open spaces between the larger particles, we have smaller spherical particles hanging out. So whether that's a silt particle in between sand grains or sand particles in between cobbles or whatever. But the point here is that some of the pore space is actually being occupied by other solid material, which will obviously decrease the overall pore space available for water to be there. This arrangement is still cubic packing, but the porosity has decreased significantly. Here on the example on the right, we have porosity of about 15%. again, because a lot of the open space between the larger grains are plugged up with smaller sediment grains. So again, this all impacts how well water is able to be accommodated into the ground. Now, there's another way to pack those spherical grains against each other. Instead of cubic packing, we have something called rhombohedral packing, and basically each of these relatively same size spherical grains are essentially stacked on one another, such that adjoining grains are kind of nudged in between the gap of the two around it. What that does is it decreases the porosity by about half compared to the cubic packing equivalent from the previous slide. And then if you also then introduce smaller sediment grains into those pore spaces, you're further decreasing the porosity from 26% on the left to about 10% on the right. So again, we're messing around with how much water can be accommodated into the sediment by not only the shapes of the particles, but also how well they're packed into each other, against each other, and if there's anything in between them. I don't think it's difficult to imagine that if instead of dealing with a perfect situation where all these sediment grains are perfectly spherical, if some were angular and whatnot, you'd actually increase porosity, because a lot of angular shapes don't pack up as well against each other typically, as opposed to this situation. So a lot of factors go into play with respect to how well the subsurface can accommodate water. Now, the discussion we've done so far is with respect to sediment. Well, let's talk about rocks, for example. So you know, there are three types of rocks, right? Sedimentary, igneous, and metamorphic. Each of those three rock types, when any of those rock types are born, they have a primary or intrinsic porosity and permeability to them, just based on how they formed and how they're made and what they're made of. So the example on the left, say a classic sedimentary rock, say this is a sandstone, right? We have sand grains packed against each other and some open pore spaces. When this sandstone was first formed, it is born with a relatively high porosity and high permeability. The middle example is an intrusive igneous rock, say like a granite, where the whole thing by definition is just an interlocking mosaic of large crystals that came from magma that cooled down. Very poor porosity, very poor permeability. There's just no open space in between those phenocrysts to allow water. So that's poor compared to the sedimentary rock for sure. And then for metamorphic rocks, well, it depends on the type of metamorphic rock. If it's like a slate or a schist, one of these foliated metamorphic rocks, you have open space between the different elongated mineral grains, which can accommodate water. But if you have a metamorphic rock that's like a quartzite, for example, it was a quartz sandstone that got baked into an even harder rock that has very low porosity permeability. So it depends on the rock. But Mother Nature can change this if you take any one of those rock types and you just break it apart, you fracture it. So this could be done when Mother Nature starts applying stresses to rocks, right? Due to you know earthquakes, right? Or anything that causes the rocks to break, right? An earthquake is a result of stresses on these rocks, but once you break these rocks up or fracture them in a number of different ways, this could happen. Those fractures are then open spaces themselves that can accommodate water where the unfractured precursor might not have been able to. So this is called enhanced or secondary porosity and permeability. And whatever rock type you start out with, if you fracture it, just fracture it all apart, you're increasing both of those things regardless. So if you have any examples there on the three bottom examples as underlying your watershed or drainage basin, again, your propensity to have flooding in that area is decreased because more of the subsurface can accommodate water. Okay, so let's switch gears a little bit here and talk about flooding caused by the rise of the water table. So by definition, the water table, which is shown here in this diagram as a red dashed line, the water table by definition represents the top of the zone of saturation or the phreatic zone. So below the water table, all of the pore spaces in the rock and the soil are full of water. And above the water table, from above the water table up to the Earth's surface, that's called the zone of aeration or the vadose zone, and all of the pore spaces in the rock or the soil are filled with air. So the water table is not a static thing anyway. It rises and falls based on atmospheric pressure. It's also not just a flat horizontal thing, meaning that it mimics the topography. So the water table will rise if to coincide with, say, the uphill slope of a mountain, for example, and on the other side of the mountain, when the slope, when you're going down the other side, the water table will decrease as well. So it's not just flat all around. It rises and falls because of the atmospheric pressure, but it also mimics the topography a little bit. Now the water table level, the elevation of the water table can also rise if you obviously suddenly introduce a bunch of liquid water onto the Earth's surface. As the arrows show, snow melt or rainfall will soak into the ground, pulled by gravity, right, directly downwards. But those water molecules are trying to get down to the water table. Ultimately, that's where they're going to end up. But if you introduce more water into this area than the soil can accommodate or the rock can accommodate, the water table will rise accordingly. And if the water table actually reaches the Earth's surface or exceeds it, then you have a flood. And you've probably seen this already if you've ever gone outside after a heavy rainfall and you're walking on your front lawn, for example, and as you're walking on your grass, it's just, water's pooling around your feet and it's kind of slushy and messy. Well, that's what's happened. The water table is essentially at the Earth's surface, and that's a swamp too, right? It's a little bit above it. So, over time, with the cessation of precipitation or snow melt, the water level and the water table will drop as all the subsurface kind of drains itself out and back to where it normally would be. So as we kind of wrap up our discussion on watersheds and drainage basins, one thing we haven't specifically discussed are the streams and rivers that come out of these things. Now a river is basically just a larger version of a stream. So the two terms are interchangeable, but if it's a really big feature, we call it a river versus a stream. But these come in basically one of two flavors. We have losing streams and gaining streams, and that simply refers to the fact that the water in either one of these stream channels is either perched above the water table, in which case it's a losing stream, right? The water in the stream channel will kind of filter through the bed of the channel trying to get to the water table, or we have a gaining stream in which the water in the stream channel itself is being fed by the water table. And this is, a gaining stream is typically why we see water flowing in, desert areas. Even the water, hasn't rained in months, but there's still water in the stream because the water table is feeding it. So the definition of a stream and a river, simply we have water moving through a confined water moving through a channel, right? And each of these channels flows out of a watershed or drainage basin into the next downhill watershed or drainage basin. Ultimately, this water on the surface is trying to make its way into the oceans, which is the ultimate low point on the planet's surface. In addition to being classified as either gaining or losing, rivers can also be classified as either meandering or braided. So a meandering river or stream, as the name implies, just kind of meanders its way across the Earth's surface. Single channel of water that's flowing, downhill, trying to find the path of least resistance, and its path is changed as different rock types of different hardnesses and resistances to the water eroding it away are encountered. Ultimately, you might have a part of this meandering channel pinched off and bypassed when the stream kind of straightens itself out. You would then call that an oxbow lake. Comparatively, we have what are called braided streams or braided rivers. Here we have still a singular channel of water, but it's not very deep, but it's pretty broad sideways, right, from side to side. So you don't have a lot of water moving through it, but you have a lot of sediment kind of choking up the channel, which causes the water to kind of, you know, cut through it here and go around it, giving it the braided look. So morphologically, those are the two types of rivers or streams. We talk about this water moving in a river or stream. Three basic things can happen. First, it can be of concern of us with respect to flooding. The water itself, and then the sediment that's being eroded away and by the flowing water, and also sediment being deposited. Let's walk through these one by one. With respect to the water in the channel itself, we can talk about the water velocity, simply the speed of the water moving through the, moving through the channel. We can talk about the discharge of waters, the quantity of water flowing through that channel at any given time. So, you know, cubic feet per second, for example. And then we talk about the water stage, and that's just the water level at some point in the actual stream channel itself. So associated, again, the associated hazards with rivers are what we just mentioned, 1, 2, and 3 here. If we take a look at a river in cross section, we can see that we have the channel itself, which holds the water. On either side of the channel is a flattened area of land called the floodplain, flattened for when the water comes out of the channel and kind of erodes over the banks, and then the bank on the other side that confine that. Usually the stream channel is underlain by loose sediment, which then overlies usually solid bedrock at some depth. This is a great example of a real world. It's both a meandering stream and a braided stream. You can see it's braided here and here, but it's meandering over the surface. This is the floodplain on either side of this huge river, which is great for farming, as you can see here. Periodic flooding of the water loads the surrounding land with a lot of nutrients and organic rich material, which are great to farm in. But the problem is whenever the floods occur and the water overflows the banks, then the floodplain is flooded. Question 3, please.
Back to you, Chris.
Thanks, Lindsay. Question 3. Watershed is another name for drainage basin. With respect to rivers and streams, you sometimes hear about this just in everyday news events and articles you run across. They talk about 100-year floods or 20-year floods. What does that mean exactly? Well, for any river or stream, there's a combination of how much water goes through any part of that channel at any given time. So it's a discharge of water. Therefore, it's correspondent to a particular stage. So the more water you have in the channel, the higher the water level is going to be, and we call that the stage. The whole idea of a 100-year flood or 50-year flood or 10-year flood is just statistics, and I've outlined it briefly up here in the upper left. So for example, if you hear the term a 25, if you hear the term, a 25-year flood, basically what we're saying here is that there's a 1 in 25 chance that the amount of water, right, the stage and discharge of the water in any given year is equal or exceeded. So that comes out to be every year there's a 4% chance that there's going to be a 25-year flood. Okay, it's just a statistics game. In real world, it's interesting to see. This is an example of the Red River of the North in North Dakota. On the y-axis we have discharge, the peak discharge, the maximum discharge here, and on the x-axis we have how many years that amount of discharge reoccurs. So there's a 1-to-1 line shown there, but you can see that, for example, a 100-year flood is defined by 25,000 cubic feet per second of water, right? If that's the discharge, that corresponds to to something that on average should happen once every 100 years. One in every 100 years that would happen once statistically. There's a 500-year flood over here on the far right of the graph. What's interesting about this is that within a 12-year span, from in 97 and also 2009, you basically had two 300-year floods that occurred within 12 years of each other. Right? Statistically, once one occurred in 97, you shouldn't have seen that much water flowing through this stream for another 300 years, but it showed up 12 years later. So just because something is termed as a 20-year flood or a 100-year flood doesn't mean it's not going to happen, the next Tuesday or the next year, or twice in the next, twice in the next month. But when the amount of water in a stream or river channel exceeds the bank and flows out, right, there are obviously flooding issues as shown here. Interesting that that remnants of floods can be seen after the water dies down and things are all dry again. This is an example of it's a picnic table stuck on top of a telephone pole that shows you the high water mark of this particular stream during this flood event. I thought it was kind of interesting. The water moving through the stream channel is obviously potentially dangerous with respect to flooding as well as just damage, right? As the flowing water is rounding curves and bends in the stream channel, it's eroding the banks away. So that's an obvious geologic hazard. Cars, buildings, boulders, whatever is in the way of it just gets incorporated into that and floated down the river. There's a house that got high centered on that bridge, so clearly geologic hazards. And then the third thing we can talk about is are the sediments that underlie the stream or river channels. And again, these are loose. These are largely loose, unconsolidated sediments that are full of water. They're just waterlogged. So there's a high liquefaction potential in that, meaning that if vibrated by an earthquake, for example, the sediment will behave momentarily more like a liquid than a solid. Anything built on it won't stand up. So therefore, it's it's not great for construction potentially, and it's also easily erodible because it's not a solid. Great example of this is the Leaning Tower of Pisa. Question is, why is this tower leaning? And the answer is it was built on very fine-grained river sediments that just aren't consolidating under the weight of that tower. So it's here's an example of a geologic hazard because of river sediments not being great to build on. So just to quickly wrap up, how do you mitigate for floods? How to prepare for them? You can't stop the rain, you can't stop the snow melt. You basically just be prepared and be informed. So there are several types of maps that you can consult that are put out also by the government. Some examples, and also just watching the news, you can see some of this stuff. This is an example of some flash flood warnings being put out on the news. Red means bad, so right. This is something to kind of keep in mind. Let's do question 4 before we finish up.
Back to you, Chris.
Okay, question 4. The probability of a 10-year flood occurring in any given year, 10%. It's 1 out of 10 chance. Okay, just to round up a few loose ends here. There are maps to show how far down the water table is, right? So if you're in an area where the water table is relatively close to the surface, the more rainfall you have, the higher potential that flooding because of the rising water table might be an issue. There are maps that are out there showing or projecting where flooding might be greatest due to just the rise in sea level from whatever cause, and those maps exist. You can even just look at a regular topographic map and understand some potential geologic hazards. A quick example here, this is Fort Leavenworth, Kansas. There's an airfield there right next to the Missouri River. You can see the floodplain next to that big meandering river. You'd think, well, it's in a floodplain, you should expect flooding, and that's exactly what happens at this place about every 40 years or so, 30 years. It periodically gets flooded because the Missouri River can't accommodate all the water trying to move down it. And again, other maps exist showing potentially hazardous areas in this case with respect to storms, right? Category 2, Category 3 hurricanes, right, where flooding would potentially be felt greatest due to those storms. So just be prepared and be able to identify potential hazards before they affect you. Question 5, please. Last one.
Back to you, Chris.
Okay, question 5. In which state was the Sherman Army Airfield located? We just talked about Fort Leavenworth. That's in Kansas. So with that being said, I want to thank you all for joining this webinar. Much appreciated. If you have any feedback, questions, comments, please email them to the email address that you see on your screen right now, pdhwebinars@atlantictesting.com.